Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Yaswant Devarakonda with us today. Hi, Yaswant.
Howdy. Thanks for having me.
Howdy. Wow.
It's the official greeting of Texas A&M.
You must be in Texas.
Mm-hmm.
Whereabouts?
So I'm in College Station right now, which is sort of right between Dallas, Austin, and Houston.
And since it is June 30th, 2022, as we shoot this, I imagine you are getting some of the same weather I'm getting here in Phoenix. So you're getting that big Gulf Coast moisture rolling up.
Oh, I can't wait for it to hit. It's been over 100 all month.
Wow.
We've been waiting for rain for a while.
Wow. Okay, we got a little rain yesterday. Last couple of days in Phoenix, we've gotten a little rain. This is the rainy season in Phoenix. This is where we get the big water drops, and the cacti love it. So succulents love it. Very cool. What is your position there?
So I am a graduate student about to start my 5th year.
Awesome.
So
pretty
excited.
Sometime this year we will be Dr. Yaswant.
Yes, hopefully. That's the plan at least.
Very cool. Very good. That'll be very nice. Cool. And Yaswant, what do you like to do for research, or what will be your general thesis topic? I guess will be the same thing.
Yeah, so I've jumped around on a lot of different topics, but right now I'm working on Type 1a supernova, particularly looking at their UV and optical properties. So we're preparing for all these big stories that are about to come up, like Rubin and Roman, that are going to find so many high redshift supernova, and all their rest frame UV will be redshifted into our optical and whatnot. So we really need to try to understand what those UV properties are like in the nearby universe to prepare for that.
Cool. So you kind of caught my attention. What other projects have you worked on?
Okay, a lot of stuff. So I've done things from high redshift galaxy evolution, working with some Lyman alpha emission galaxies. I've done a little bit of side projects on gravitational lensing with clusters. I did another side project with exoplanets and instrumentation. Spent 2 years in grad school working on supermassive black holes. So I really jumped around from topic to topic a lot.
Eclectic.
Yeah.
It's very good. It's very good. It's good to be broad. Good to be broad. And that is then going to bring us to this very awesome AJ article. It's open access, people. Go get it for a freebie. Go grab it. Comparisons of Type 1a supernova light curves in the UV and optical with Swift ultraviolet optical telescope. And Yaswant, take us away.
Yeah, so it's quite a lengthy title, but we felt it was important to have all that information on there. So as I mentioned earlier, we're doing a lot of this work in preparation for upcoming Rubin and in the next couple of years, Roman, hopefully, observations of high redshift supernova.
Right.
And so we're trying to get a better understanding what the UV properties of supernova are nearby. We know optically they do a lot of really nice things for cosmology and whatnot, that they're standardizable. In the infrared especially, we know that they're even more standardizable. They're less affected by things like dust and other effects in that infrared. And so there's been questions of, okay, what happens when you go to the UV? Some models predict that, because there are more iron lines in the UV and stuff like that, they should be more affected by effects of metals and whatnot. And so maybe they won't be as standardizable. And there have been a few studies to look at them, but most of the studies have very limited data sets. So no one's done a full statistical comparison yet of the UV and optical. And a lot of the current models as well don't go far into the UV. So that's been another issue with studying the UV, is that the models aren't quite there yet.
Okay.
And so we're trying to say, all right, let's take some optically trained models here and see how well we can compare the UV and optical light curves using some optically trained models.
Okay.
So first, let's check to see, do these optical models even fit the UV light curves? And if they do, what does that say about the difference between the UV and the optical? How different are they now that we have a common set to measure them against?
Right.
And so that's what we're trying to do. So we have these 97 supernova from the Swift Observatory that we've taken. And we're using a fitting technique called FPCA. If you want to go down to figure 1, yeah.
Sure.
So the idea here is that we had a colleague who published a paper in 2018, et al. 2018, on this fitting technique. So it's principal component analysis, but it's a different type called functional principal component analysis, which handles time series data a little bit better,
Okay.
which is useful for supernova light curves.
Yes.
And so they looked at a bunch of BV, R, and I data for type 1a supernova to try to make models where each principal component affects a different part of the light curve shape. And then if you just linearly add a mean light curve shape plus each of the different weights for the different templates, you can in theory fit any light curve. Of course, this is changed in BV, R, and I data, not UV data.
Right.
And so what we're trying to say is, okay, one of the cool templates they made was what they're calling the band vague template. The idea being that in the future, with Rubin and Roman, you're going to observe all these supernova. Maybe you don't have the register information quite yet, so you don't know what the rest frame is, but you want to get a quick fit out there anyway. So how well can you do just a rough fit, making no assumption of what the rest frame emission is? So that's this band vague template that we're using here. So this is an example of what the effects of the first three principal components have on the templates for a set of common B band weights and stuff like that. So in the first principal component, that mostly seems to affect the decline rate, especially at relay times. The PC2 weights, which seem to be the most important weight, we'll get to that later, affect the decline rate nearby, sort of the almost stretchiness of the light curve.
Yeah.
It certainly has the biggest impact on things like the 15-day decline rate, which is super important for cosmology studies and stuff like that. And then the third principal component weight seems to mostly affect the rising portion of the supernova. That's where it has the biggest effect.
Yeah, got a nice bend there. Okay.
Yeah. Cool. So that's the basic idea for this fitting method. There are additional principal components that we decided not to include, and I'll talk about that in a second. Okay. But actually, if you want, I can scroll to figure 4. I can talk about that real quick.
Sure, let's do figure 4. We go nonlinear. It's great. Figure 4. There we go. Bootstrap.
Yeah. So this is one of the ways we did to test, okay, what is the proper amount of principal components to fit in our case? So we had an option to go up to 4. We ended up going with 3 after doing some bootstrap testing. Okay. Some of the issues to statistically decide which version works better is the fact that a lot of our supernova aren't super well observed. We don't have enough data points for each supernova. What we can do is we took 4 supernova that were really, really well observed, and we did bootstrap draws, which is useful because you're basically simulating different cadences for observing by doing this bootstrap draws for these supernova that simulate what it would be like in reality. So using that, we can compare to see how well are we doing in the different fitting functions using these bootstrap draws compared to what we did with the full data sets. And what we found using our model comparison, which we use the Akiki information criteria here, is that you don't really add any major benefit from that 4th PC score versus that 3 PC score. We're adding extra complexity to the model, but not necessarily improving our fitting. Okay. In the 2 to 3 region, it's sort of a coin flip. And so we said, all right, let's just go with 3 for a full model. And then in the future, maybe if you're doing individual supernova, that's when you can go check them individually to see which one's better. But if we're doing the whole set, let's just do 3 for the whole set based on that.
I got it. Very good.
And so if you scroll back up to 2 now.
Let's go to 2. There you go.
So this is... I mean, let's be honest, it's a cherry-picked example, but who doesn't cherry-pick their examples when they're making papers, right? So this is 2011 BY, which is one of our best observed supernova, using the 3 template model in all 6 of the Swift filters. So the UVW2, UVM2, UVW1, UV, and V. And in all 6 filters, we see we have a pretty satisfactory fit to the observations here. Yeah. Which is a good sign that things are going all right, at least.
Yep, at least on this one.
At least on this one, right. Well, so figure 3, then we looked at, all right, if you look at the R² value, which is one measure of goodness of fit, we noticed that overall, it's still pretty satisfactory. So in this box plot, and this is the style we use for all box plots here, the upper and lower limit on the box is the 25th and 75th percentile. Got it. The tick marks on each end is 1.5 times the interquantile range.
Okay.
And then the little notch in the center is the median and the
Yes.
error estimate on what the median is.
There you go.
And so we see that for almost all of these cases, in almost all these supernova, we have a very, very high goodness of fit value. So we're pretty happy with what we see so far.
Yeah.
There are some issues. For instance, you see in the UV M2, there's a quite large,
Bigger. Yes.
a little bit larger, but that's because the UV M2 is it's the narrowest filter that we have here. It has the least flux going through the filter in general, and so there's much larger observational errors in the UVM2.
Yeah.
And in a lot of cases, there's a lot of non-detections in the UVM2 where we would have detections, for instance, in the B band.
Ooh, fair enough. Okay.
So that's some stuff we're trying to deal with here.
Yep. Okay. Thanks for explaining that shape.
Yeah. So we can move on to the next box plot, which would be figure 5, which all the information in the tables is basically shown in figure 5 as well.
Okay, let's see what we got here.
So this is when we compare the PC scores on the delta M15, which we just measured directly from our model. Each of the bands, we measure what the spread and the parameters are. This is a measure of the diversity of light curve shapes. So if we assume, for instance, we saw the PC1 weight affects mostly the late time decline. We saw the PC2 weight affects mostly the near peak decline and stuff like that. So if you use this as a proxy for the light curve parameters, we can look at what the diversity of the supernova is in each of the bands.
Okay. I'm with you.
So what we noticed is that relative to the B band, which is what we're using as our standard for what we want, because that's what's most constantly used in cosmology for standardization.
Yes.
In the PC1 and the PC2, there is no difference in the overall spread of parameters. So that's basically saying that the diversity of light curve shapes in the UV versus the B band isn't actually as different as previously thought.
Got it. Okay.
Yeah, so that's what these are saying. The PC3, there is a much larger difference. And so again, the PC3 is looking at the light curve rise, but that's also where you have the least amount of data. And so there's a lot of stuff going on there. And then the delta M15, which we measure directly off of our model, just what is the magnitude at day 0, what is the magnitude 15 days after the peak, just subtract the two from the model. And we see that just like the first principal component and the second principal component weights, the diversity is pretty similar between the UV and the B band. Particularly, which is really interesting, the UVW2 band has the strongest tie with the B band, which is pretty interesting. So that's sort of the mid UV range. There seems to be slightly more diversity in the UVM2 and UVW1 relative to the B band. Statistically similar based on some of the tests we did, but still, it seems to be better in the UVW2.
Yeah. Okay. Cool. I got it. I'm with you.
Yeah. And so actually we can go on to figure 6 and we can look at some of the other stuff we looked at. So now we said, okay, we know that the diversity is similar. Are they correlated between supernova? So here we have 23 supernova of our 97 that we had a W2 and a B band fit for. That is satisfactory. And then we use this method called LinMix. So this is a MCMC linear regression model that we used to try to estimate what the correlation is between the different filters for the different scores. So in this case, this is the UVW2 and the B band piece 2, which again controls the near peak decline rate. We find that they are very, very strongly correlated statistically. The exact shape is probably not a linear shape. You may notice that it's not exactly a great fit, which is we expected that it probably wouldn't be completely linear. But for a first pass at attempting to measure what this relationship might be, at the very least, it draws your eye to what that correlation is.
Band is, yes.
Exactly. And there's a lot of questions as well over, if you look at those bottom two supernova on the bottom left corner there, there's a lot of questions on, okay, are those outliers or are the other two low supernova over out there, are those outliers? We
Right.
don't know which one of these are actually outliers or not. We're just putting everything on there. And so if you
Fair
assume
enough.
some of those just like weird supernova with different physics, some outliers, maybe the shape of this correlation will change. But at least now we know that there is a correlation and that this is something we should be looking into more. But outlier selection will be a major thing we need to figure out for future works.
Okay. Very cool. Got it.
And so then the next 4 plots are basically all of the correlations then that we found in all the different filters. I can just sort of breeze through those a little bit.
Okay, let's go figure 7. All right.
Yeah. So figure 7, this is all of the filters now relative to the B band for the first principal component score. And here I only plot the correlation, so the Lin-Mix relationships, if there's a statistical correlation based on Spearman testing.
Yes.
Which is why the M2 and W1 filters we didn't plot that Lin-Mix regression. And so here we see that there's a pretty clear correlation between the U and the V and the B. The UVW2, it depends on what you consider an outlier or not, but sure, something might be there. The UVM2 and the UVW1, it doesn't look like there's much of a correlation, but there's also a lot of points with the really large errors. Yeah. And so that might be skewing things. Again, we don't know anything about outliers yet or not. So that's pretty interesting. But if you take this at face value, this would suggest that at late times, there's not a strong correlation between the UV and the optical, for instance, if you take it at face value.
Yeah, okay.
And then the next plot would be for the PC2 for all the supernova.
Here's our AIC. There we go.
And so this is sort of the really interesting one. We find a very, very strong correlation in all the filters, let's say the B band, for the principal component 2 weights. So this is the near peak decline and sort of the stretchiness almost of the light curve. So again, taken at face value, this would suggest that the near peak decline rate in the UV and the optical is strongly correlated. Perhaps the stretch factor is also strongly correlated, which would be really, really good for doing future cosmology studies. If you can correlate the decline rate in the B band and versus the UV and tie those together this way, then when you're doing cosmology with the UV, you have something for it to stand on.
Nice.
So this is something that's really, really interesting.
Yeah, that's very nice. Cool. Very
and then the next figure 9, is the third principal component. In this case, there's absolutely no correlation, it looks like, between the UV and the optical. And there's sort of a weak correlation in the V and the U, but also there's some issues with what the PC3 is measuring. We're mostly just including it because it makes some of our fits better, but it's not necessarily the most trustworthy part, based on the fact that it's only looking at a very small part of our model light curves to begin with, in phase space at least.
The rise.
Right. It's mostly correcting for smaller deviations in later parts of the light curve. So this is not too surprising.
Yeah, then it's not so surprising. These are all fairly low.
But the next plot is the delta M15 measurement. So this is going to look a lot like that PC2 plot here, where we do find pretty strong correlations across the board again. If it's completely linear, we're not completely sure, but it looks somewhat linear.
Trend. Yeah. There's a
but
trend.
They do seem to trend. And so that's some of the interesting things we're seeing here is, again, it looks like there is a trend, the delta M15. And so maybe this will be useful for cosmology. This doesn't mean that we can do pure UV cosmology studies yet.
Right.
But if you have multiple bands, then we can do some sort of multicolor analysis and use the fact that they're correlated in some way to set constraints on what the relationships probably are, or what the true properties probably are.
There you go.
If you measure a certain B band delta M15, you know based on this relation that the UVW2 decline rate must be within a certain range now,
Yes.
at the very least.
And
and vice versa. So that'll be useful for that'll be somewhat useful for future studies at least.
Absolutely. Very nice.
And then the sort of final plot that I wanted to talk about is that plot right there.
Yeah.
So this is something that popped up. I was just playing around with the data set, trying to figure out what else I can get out of it. And so this is something interesting that I noticed. If you plot where the peak of the light curve is in days relative to the B band, there seems to be a trend where supernovas, type 1a supernovas, peak earlier in the UV relative to the B band and later in the V band. This is something that's been noticed, but I'm not sure if anybody's statistically shown this in any way. So on average, in the UVW2 and the U band particularly, there's best constraints there. They seem to be peaking about 2 to 3 days before the B band in the UV. And in the V band, it peaks about 2 days later on average than it does in the B band.
Yeah.
The other interesting thing we found is if I looked at these outliers, those little circles, outliers, all of the supernova that peak earlier than expected in the UV or earlier than average in the UV, so those 3 supernova and a couple others that aren't popping out, they're all supertron sugar mass candidate supernovas, which is really interesting. And we don't find any. I went through all the supernova sample, and those are the only super C candidates. The other supernova that are in the normal range, none of those are super C candidates. Those all seem to be normal type supernovas. And so this could suggest some interesting physics going on with these super C candidates, super C supernovas, that something is happening maybe that's causing them to rise very, very quickly in the UV relative to the B band.
Oh, that's interesting. Okay, cool.
Yeah. Cool. So that's something that we sort of throw out there at the very end, just to be like, we don't know what's going on. But
tantalizing.
Again, the UV models aren't quite where the optical models and stuff are there. It turns out that with all the issues with metal blanketing and stuff in the UV, it gets pretty difficult. But this is at least pointing to some places where people can look.
Yeah, very nice.
Awesome. But that's sort of the summary of the paper, is that, if you look at this sample, we see that statistically speaking, the diversity of light curve shapes in the UV is not that different from what it is in the optical, which is contrary to what other people have found. But other people's studies were, sample of 5 or 10 supernova. We're looking at 97.
That's great. That is awesome.
And we also found that they're strongly correlated, which will be really useful for like I said, for upcoming cosmology papers, as well as this shift in the peak date, which is also actually really, really useful for when you're doing modeling and stuff and try to figure out where the peak actually is. That can put strong constraints on what might be unreasonable.
Yeah.
Which is actually something that I'm already benefiting from right now in my current project as well.
Oh, well, let's get to there. So first of all, Yaswant, I want to thank you so much for walking us through this very awesome paper on 97 SN1A in the UV. Very cool. Thank you.
Thank you. I'm happy to talk about it.
Sure. And you mentioned it a couple times. So one, you just mentioned what you're working on now. But I just want to ask, where do we go, let's say, over the next 2 to 5 years? Is there a possibility of getting 197 UV light curves for the 1As in multiple bands? You mentioned the Roman telescope and the Rubin telescope. Is there other theoretical models that could be done? Just kind of where do we go with this topic over, let's say, the next, well, certainly by the time you graduate, and over the next couple of years?
Yeah, so there's a couple of things that we can be looking at. One is, as I mentioned quite often, on the modeling aspect, there's not a lot of robust UV models, not to the level that we have optical models yet. So there's some work needing to be done there.
Good.
If you look at popular fitting routines such as SALT or the multicolor light curve fitters and stuff like that, they don't really extend down into the UV yet. So a lot of that has to do with the fact that we don't have a robust training set in the UV for this. And also for physical models, there's some physical models, but none of the physical models we have so far have been able to super reliably replicate what's been observed.
Okay.
And so there's still some work that needs to be done there.
Nice.
On the observation side, like I said, it definitely benefits to have more supernova, if at the very least, just so we have something to train future models on and whatnot. Some of the issues is that looking at, the nearby universe UV stuff, SWIFT is basically the only telescope that's capable of doing this type of UV time domain stuff.
Right.
And so all of this is dependent on if we get enough SWIFT time to do these kind of studies. And if SWIFT is able to stay up and stay fueled and stay functioning.
Right.
Because if something happens to SWIFT, then that's kind of the end of this until somebody launches something else. So that's some of the issues we're working with. There are a lot of constraints here. Yeah, hopefully.
Fingers. Stuff keeps going. Yep.
But I think, yeah, we definitely benefit from having more nearby UV observations so we can better understand what's going on here, and having the models to explain the observations we're getting. That's sort of been a sticking point in most of my projects. I'll especially like this last paper, my current paper, a couple of other would-be papers in between sort of all reached the ending point when we're like, all right, what models can we use to describe what we're observing? And well, there is none.
Dearth. Right.
My background is mostly in statistics, not physical modeling, so I'm not quite ready to dive into that just yet.
Yep. Well, there are people out there who can potentially do it.
Yeah, hopefully. But my current project is some of the stuff that we've been folding in with what we're working now. We're using SWIFT and Hubble observations of Type 1a supernova, about 20 or so Type 1a supernova, with the hope of building the first Hubble diagram bridging UV and optical data and extending the H0 measurements of Type 1a supernova out into the Hubble flow as well.
Oh, nice.
And so that's what I've been working on recently, and that's why these relations that I've found are really, really useful when I'm trying to fit our supernova. A lot of them we only have 3 observations for, and you're trying to fit a light curve to that. It's very, very difficult. But if you can fit it somewhat successfully in one filter, and then the relations to the other filter, you can add constraints over what's reasonable to expect, at least. Based on the timing, based on light curve shapes and stuff. So that's been really, really useful for that kind of thing.
Cool. Well, I look forward to seeing that.
Yeah.
That article coming up. Very nice. Cool. All righty, Yaswant, thank you so much for walking us through your lovely paper once again. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye-bye.
Well, now he brings in his drink.